Welcome to this detailed engineering masterclass on air receiver tank design. We will cover the design of a 5,000-liter air receiver tank. Most engineers design air receiver tanks completely wrong. They either oversize it, waste money, or worse, underdesign and risk failure. What if I show you how to design a 5,000-liter air receiver tank from scratch, with exact volume calculation, shell sizing, and thickness using ASME and IS codes? No guesswork, no shortcuts, just real engineering calculations used in actual projects. By the end of this video, you'll know exactly how to decide tank diameter, shell length, and required thickness for different materials. This is not theory. This is how real design engineers work. We begin with Step 1, tank volume sizing. The objective is to design the tank for a required storage volume of 5,000 liters, which is 5 cubic meters. We will use basic geometry formulas for calculation. This includes the volume of the cylindrical shell, where V equals volume, meters cubed, R equals internal radius, meters, L equals straight shell length, meters, and the spherical cap, where H equals height of dome, meters, R equals radius of tank, meters, which is the dish end volume. The total tank volume is the sum of the cylinder and the top and bottom head volumes, where V total equals V cylinder plus V top head plus V bottom head. In case 1, we set the shell diameter at 1.4 meters. Using the input data, diameter, D, equals 1.4 meters, radius, R, equals 0.7 meters, bottom dome height, 0.3 meters, top dome height, 0.2 meters. For radius and dome heights, the calculated volume for the bottom dome, where V equals 1 over 6 times 3.1416 times 0.3 times 3 times 0.7 squared plus 0.3 squared, is 0.245 cubic meters. And for the top dome, where V equals 1 over 6 times 3.1416 times 0.49 plus 0.04, is 0.159 cubic meters. The total dome volume is equal to 0.245 plus 0.159 equals 0.414 cubic meters. Subtracting this from the total required volume of 5 cubic meters gives a required cylinder volume of 4.596 cubic meters. The shell length is calculated to be approximately 3.0 meters, where shell length calculation, L equals V divided by pi r squared, equals 4.596 divided by 3.1416 times 0.49 equals 4.596 divided by 1.539 equals 2.99 meters, approximately 3.0 meters. Our final dimensions for case 1 are a shell length of 3,000 millimeters with a 1.4 meter diameter. Moving to case 2, we try a larger shell diameter of 2.2 meters. With the corresponding radius and dome heights, the bottom dome volume is where V equals 1/6 times 3.1416 times 0.3 times 3.7 squared equals 0.58 cubic meters, and the top dome volume, where V equals 1/6 times 3.1416 times 0.2 times 3 times 1.21 plus 0.04 equals 0.38 cubic meters. The total dome volume for case 2 is 0.96 cubic meters. The required cylinder volume is 4.04 cubic meters. This results in a calculated shell length of approximately 1.1 meters. The final size for case 2 is a 2.2 meter diameter with a shell length L equals 4.04 divided by 3.1416 times 1.21 equals 4.04 divided by 3.80 equals 1.06 meters, or approximately 1.1 meters. Step 2 is thickness design. Common design data used includes a design pressure of 1.0 megapascals, a joint efficiency of 1.0, and a corrosion allowance of 3 millimeters. We will evaluate 2 geometry cases, A, 1.5 meter diameter, and B, 2.2 meter diameter. What is corrosion allowance, CA? Additional thickness added to handle material loss during service life. Typical, 3 millimeters for industrial compressed air systems. We will use design formulas from the ASME code for cylindrical shells. T equals P times R divided by S times E minus 0.6 P, and T equals P times D divided by 2 times S times E minus 0.2 P for ellipsoidal heads, and T equals P times D divided by 2 times F times eta minus P is for the IS 2825 code for cylindrical shells. The variables T, P, R, D, S/F, and E/eta are defined for thickness, pressure, radius, diameter, allowable stress, and weld efficiency. For Material 1, SA 516 grade 70, with an allowable stress of 138 megapascals. Case A, 1.5 meter diameter, requires a thickness of 10 millimeters for both the shell and the head. Case B, 2.2 meter diameter, requires a thickness of 12 millimeters for both the shell and the head. The calculation is presented below. In Case A, for material SA 516 grade 70, with an allowable stress of 138 megapascals, we will calculate the required thickness for both the shell and the head for Case A, which has a diameter of 1.5 meters. Shell thickness calculation. We use the formula T equals P times R divided by S times E minus 0.6 P, where T equals thickness in millimeters, P equals internal design pressure in megapascals, R equals internal radius in millimeters, S equals allowable stress in megapascals, E equals weld joint efficiency. Substituting the values, P equals 1.0 megapascals, R equals 750 millimeters, S equals 138 megapascals, E equals 1.0. Numerator, P times R equals 1.0 times 750 equals 750. Denominator, S times E minus 0.6 P equals 138 times 1.0 minus 0.6 times 1.0 equals 137.4. Therefore, T equals 750 divided by 137.4 equals 5.46 millimeters. Including corrosion allowance of 3 millimeters, T total equals 5.46 plus 3 equals 8.46 millimeters. Final selected thickness, 10 millimeters. Head thickness calculation. We use the formula T equals P times D divided by 2 times S times E minus 0.2 P, where D is the internal diameter. Substituting, D equals 1500 millimeters. Numerator, P times D equals 1.0 times 1500 equals 1500. Denominator, 2 times S times E minus 0.2 P equals 2 times 138 times 1.0 minus 0.2 times 1.0 equals 275.8. Thus, T equals 1500 divided by 275.8 equals 5.44 millimeters. Including corrosion allowance of 3 millimeters, T total equals 5.44 plus 3 equals 8.46 millimeters. Final selected thickness, 10 millimeters. Design parameters. Design pressure, P equals 10 bar or 1.0 MPa. Joint efficiency, E equals 1.0 for fully radiographed weld. Corrosion allowance, CA equals 3 millimeters. Why a higher plate thickness is selected? In practice, plate thickness is selected based on standard available sizes, such as 8 millimeters, 10 millimeters, and 12 millimeters. Mill tolerance may reduce the actual thickness slightly, typically by about 0.3 millimeters. Additional margin is also required for welding and fabrication. Therefore, as a good engineering practice, thickness is always rounded up, not down. In Case B, for SA 516 grade 70, the shell calculation requires 8 millimeters plus the corrosion allowance, totaling 11 millimeters, rounded up to a 12 millimeter plate. The head calculation also results in a 12 millimeter final plate selection. Now for Material 2, IS 2062, with an allowable stress of 117 megapascals. Case A, 1.5 meter diameter, requires a 12 millimeter thickness for both the shell and head. Case B, 2.2 meter diameter, requires 14 millimeters for both. For IS 2062 Case A, the required shell thickness, including corrosion allowance, is 9.44 millimeters, resulting in a final plate selection of 12 millimeters. The head calculation is also 12 millimeters for the final plate. For IS 2062, Case B, The shell calculation requires 9.45 millimeters, including the corrosion allowance, which rounds up to a 14 millimeter plate. The head calculation similarly results in a 14 millimeter final plate selection. We move on to Material 3, SS304, with an allowable stress of 120 megapascals. For Case A, 1.5 meters, the required shell and head thickness ranges from 10 to 12 millimeters. For Case B, 2.2 meters, the required thickness ranges from 12 to 14 millimeters. For SS304, Case A, the shell and head calculations, including corrosion allowance, are approximately 9.28 and 9.26 millimeters, respectively. Both are rounded up to a final plate selection of 10 to 12 millimeters. For SS304, Case B, the shell calculation is 9.21 millimeters, and the head calculation is 9.17 millimeters. Including corrosion allowance, both round up to a final plate selection of 12 to 14 millimeters. This final comparison table summarizes our findings. The material selection significantly impacts the required plate thickness. Materials with a higher allowable stress, like SA516GR70, result in a thinner plate and potential cost savings. In real industry practice, design is not just calculation. It involves fabrication logic. Vendors rarely use the exact calculated thickness. For medium tanks, 12 to 14 millimeters is typical due to standard plate availability, manufacturing tolerances, and long-term durability. The key takeaways are to correctly calculate volume and pressure thickness using codes. Always add corrosion allowance, and remember that higher stress materials mean thinner plates. Fabrication reality requires rounding up to standard plate sizes, combining calculation with manufacturing wisdom. You have now mastered every formula, assumption, and calculation step, understanding how pressure vessel thickness is engineered, not guessed. This content is for educational purposes only. Final designs must be verified by qualified engineers. Thank you for joining the Air Receiver Tank Design Masterclass.